Welcome everyone. Welcome everyone. Before we start, I'm just going to give it a few more seconds just to make sure that everyone has transferred into this webinar room. It shouldn't take too long. I can see that people are slowly entering the room, so I think it should be good now, so we can commence. Thank you. So good morning and good afternoon, everyone, and thank you for joining us today for this second XDFM Methanol Engine webinar. My name is Trianne Hoopshally, and I'm the Senior Brand and Marketing Manager here at WinGD. Here to present to you today is WinGD's General Manager, Application Engineering, Marcel Ott, and Senior Product Manager, Leif Knipstrom. Yep. So just a few points before we start. Oh, yes. Please say hello, guys. Just a few points before we start. Your microphones are automatically on mute so as not to interrupt the presenters during the webinar. If you have any questions during the presentation, please write them in the chat box, just to the right of your screen there. These will be answered in the Q&A at the end of the webinar. For those who would like a copy of the presentation slides, at the end of the webinar, you will be redirected to a short survey where you can opt to have the slides emailed to you. Well, that's it from me. We're going to play a quick video before I hand you over to Marcel. So thank you, everyone, and see you again in the Q&A.
Okay, hello, good morning, good afternoon also from my side. Welcome to our second webinar on WinGD's XDFM methanol dual fuel engines, and thanks for joining this session. As Trianne mentioned, my name is Marcel Ott. I am in charge of application engineering within WinGD sales. So I'm in charge with my team for the technical sales support and promotion. We're happy to have you with us today for this webinar on one of our latest product series, the dual fuel methanol engines. You have seen a bit of a teaser as an introduction in the video, and we would like to show you a bit more in detail where we stand and what this product actually is. So first of all, before going into any engine-related details, a few general considerations on methanol as a fuel. As you all know, methanol is one of the possible pathways towards a carbon-neutral shipping by 2050, as IMO imposes or requires with the regulations that are in place. I think it's important to mention that methanol actually must be from green renewable sources to achieve that, and that's obviously something that's out of the engine designers or makers scope. So what we're trying to do here is to make engines available that do manage to run on all these fuels that are coming. Methanol is one of them. A few general words on opportunities and challenges here of methanol as a fuel, or methanol in general. Generally, I think it's fair to state that methanol is actually fairly simple to handle. So compared to LNG, as an example, it doesn't require cryogenic storage, which means that the fuel storage and supply systems are actually much more simple on board a vessel compared to LNG. Another positive aspect is that it's actually not or little toxic compared to ammonia, especially. That's an advantage. So even if there is contact with methanol, it's not an issue, while this is something that on ammonia as fuel requires definitely more attention. And then also, as a result of the first 2 points, this means that if you look at a vessel, this will come at relatively little additional capex compared to a conventional fueled vessels, or definitely on a lower cost basis than other alternative fuels. There are other points, challenges, of course, with methanol as a fuel. First of all, starting with the availability of green methanol. As I said in the first introduction point, it's essential to use green methanol to actually have a positive impact on the CO2 or greenhouse gas emissions. And the availability of these green fuels, I think, is going to be limited in the near future, for a while at least. Another point is that the production of methanol actually is somewhat less efficient compared to ammonia, for example, because methanol still includes carbon, so it actually requires a carbon source for production, which again means that part of the production process is some kind of carbon capture in order to provide that to the production of fuel. And that obviously reduces the production efficiency to a certain extent and has an impact on pricing. So just a few very general aspects on methanol as a fuel. From an engine point of view and from a combustion point of view, I think we can clearly state that methanol is a fairly straightforward fuel. So it's relatively simple to use it as a fuel for an engine, as many of the aspects are close to what we have always known with the diesel engines. We would like to also show an overview here of the references that we have managed to secure, and despite the fact that we have only entered this methanol-fueled market, we have already seen a number of orders firming up. You may have seen this first order for a 16,000 TEU vessel series with our largest engine, the 92 DFM, for which the first engines are going to be delivered from Q1 25. Additionally, we are happy to announce that we have just received a second nice important reference project with 82-bore methanol engines for a series of 9,000 TEU container vessels with first engine deliveries from Q3 2025. That already shows that the portfolio is expanding, and that also goes for the last bullet that you see here. We have also just recently contracted an upgrade package for a series of 52-bore short-stroke engines that are going to be upgraded from diesel to methanol. So also that is coming. Talking a little bit about the introduction plans for the portfolio. Obviously, we are aiming to have the full portfolio of engines available as methanol versions. And what we see here is the latest plan that has been communicated also with our engine builders in terms of availability of documentation and drawings. Again, you see the three firm projects that were listed on the previous page with 92 82 and 52 bore engines, and then we have the mid-bore engine type 6272 also on the list here to be coming in the near future. With this portfolio, we will actually be able to cover the vast majority of two-stroke applications, and I think it will put us in a good position to have an engine available for almost every application possible. So a few of the key features of the XDF-M and what are the features that describe these engines. First of all, I'd like to mention that we do actually guarantee highest efficiencies of these engines in both diesel and gas mode, as we will see. As this is inherited of the latest diesel engine design. So the engines are actually based on the very latest fully up-to-date diesel engine versions, which already provide, let's say, very competitive efficiencies. And the same is valid for the methanol versions. And we believe that this is actually of very big importance, because many of these engines may run quite some time on conventional fuels. So diesel efficiency is important. But also running on methanol fuels, one has to expect the fuel cost to be significantly higher than what it used to be in the past. So a high efficiency in both modes is actually essential. Our engines come with very low pilot fuel quantities. We are talking about levels of below 5% at high engine load. That portion is obviously increasing a little bit when the engine goes into part load, so the relative amount is a little higher there. But low pilot fuel quantities, we believe, is important because it allows to have 100% carbon neutral fueling with a small amount of, here it's called the green pilot fuel, that could be, for example, a biofuel, which is also costly, so to lower the amount, the better. We also follow a very simple design concept on these engines, as you will see on Leif's part of the presentation later on. Again, these engines are based on the diesel engine design, and we have only added an injection system for methanol on top of the existing design. You will see more details on that. And that concept actually allows or provides a very high level of reliability. We can ensure the full redundancy of systems that we have from the diesel engine design, and by that optimize or ensure operational safety of the engines. Again, I would like to talk a little bit about the general design concept. I mentioned before that the XDF-M is actually a diesel engine plus a methanol injection system. I think it's important to understand that the biggest part of the engine, majority of all parts and systems on the engine are actually totally identical with what we have on the diesel engines that are very well established. Yeah, that makes, of course, things much more simple, and also in terms of logistics and so on. Additionally, we can guarantee that we have the same diesel mode efficiency as a regular diesel engine. So there's no compromise in that. The same fuels can be used when running in diesel mode, so ranging from distillate fuels to different heavy fuel oil types. And we have the full redundancy, as we saw before, the full redundancy of a diesel engine that people are used to. In methanol mode, we can guarantee the same power output as a diesel engine and the same performance, so similar efficiencies that are achieved there. We are also using the same emission abatement concept, so we're working with SCR catalysts on these engines, same as what we do on the diesel engines as a standard. A few words on the installation related aspects, particularly here on the fuel supply system. For methanol as a fuel, we actually handle this in the same way as what we do for other types, conventional fuels or LNG as a fuel, as that WinGD is actually not the supplier of the system, of the fuel supply system. What we do is that we provide kind of system proposals, and we provide recommendations and requirements towards makers of fuel supply systems. And that means that there is actually a wide range of suppliers available or going to be available in different builder countries. So there is a good chance for shipyards and owners to select their preferred suppliers that can deliver systems according to our specifications. Generally, we can say that the fuel supply systems for methanol are relatively simple because, again, there's no cryogenic handling of fuels and so on, no vapor formation. So things are relatively simple, and you see from the main parameters here, supply pressure of 13 bar in liquid form, 25 to 50 degrees C, that this is relatively straightforward. A few words on the more on the operational aspects. You can see the illustration here showing the different fuel modes that are available on these engines. Obviously, we have diesel mode that covers everything from start to 110% overload operation. For methanol mode, the available operating range is between 10 and 100% power, and the system is fully designed to allow operation in that range. And as you can see, the lowest bar transfer to methanol can take place between 10 and 80% power, which is fairly or very much the same as what we have on LNG dual fuel engines, for example. There is a seamless transfer between fuel modes. So as long as the engine is between 10 and 80%, it can seamlessly transfer between the modes. And obviously, we also have an instant trip available from methanol mode to diesel mode at any time, also as a safety feature in case something is not working as intended. Start and stop and overload running is done in diesel mode, as we saw. That's partly due to class requirements and also to keep the system simple, straightforward, and reliable. All the engine or the controls of the system is actually integrated in WinGD's latest generation WISE engine control system, and no additional hardware is required for that. Actually, the systems that we have on the latest diesel engines can be used also for methanol and other dual fuel engines. I'd like to highlight a couple of slides here on the available documentation. We have been intensively working on the shipyard documentation in the last months, and you can find on our webpage that this material is all publicly available. You find the link here under which we provide material for both methanol and ammonia engines. Looking at the scope, you can see in the list here we have what we call the concept guidance for XDFM. So the concept guidance is kind of a generic document that describes the overall system from tank to the fuel supply system to the engine and how the interfaces look like. Then we have the Marine Installation Manual, which is a very important document for ship designers and shipyards, mainly for installation planning of the engine in their ship design. And same is what we call MITS, the Marine Installation Drawing Set. So that's all available online for a number of engine types. And please take your time and find that on our web page. The same actually goes for performance data. We have what we call the GTD, so General Technical Data. That's a tool that provides the full set of performance data, so consumptions, exhaust gas data, ancillary system layout requirements, and so on. So that tool is now updated and released with the 92 DFM. We're including that engine now, and other types are following in the coming months. Meanwhile, if there is a need for performance data for an engine type that is not in GTD, please contact WinGD and we can provide a set of data for that on a project-specific basis. So with that, I would like to conclude my part and hand over to my colleague Leif, please. I'll be back for the Q&A session then.
Thank you, Marcel. Good morning, good afternoon, also from my side, everyone. So my name is Leif Knipström. I'm product manager for these engines. And so that means that I work with the product definition and define the requirements of the engines, and I also support the product launch activities. So I will now give you a small update of the engines, let's say bit more technical details, and also the status of the development. So looking into what does methanol mean for the engine? What kind of modifications do we apply to the engine compared to a normal diesel engine? So most importantly, we apply an additional methanol fuel injection system. And in order to enable this, we will need a new cylinder cover with some small modifications. We need additional fuel injectors. I will show that more in detail later on the slides. Also, to drive the system, we will need an additional servo oil rail because this is a pressure amplified system, and we will need then this additional oil rail. We will also have to adapt the engine platforms and the piping. There will be quite a number of additional fuel pipes and also oil pipes needed for this system. And then to drive the system, we'll need an additional servo oil supply unit as well. And we also have to do torsional vibration calculations to verify the methanol combustion. Methanol combustion and diesel combustion, they are close to each other, but since both are diesel cycle, but they are not let's say heat release is not exactly the same. And this means also that the shaft line and has to be checked against torsional vibrations. Additionally, in the external system, we will also need a methanol fuel supply system, including a fuel valve unit, which is controlling the pressure and the supply of fuel to the engine. Then looking into the methanol system on a more schematic level, we have here in the middle a high-level schematic showing the system on the engine. So we start from below. In the middle, we have an additional servo oil pump, which is using normal engine system oil, delivering this oil up to a servo oil rail with a pressure of up to 300 bar. Then we have servo oil pipes going to each cylinder to a pressure amplifier where we can increase the methanol pressure from 13 bar. Methanol is supplied with 13 bar to the engine, and we can, in this pressure amplifier, we can increase the pressure up to 600 bar. And then we have normally we have 3 injectors per cylinder of methanol injector, in addition to the normal diesel injectors. And this is, that's more or less the high-level description of the system. Looking into it a bit more in detail, this is the cylinder cover. Here you can see the cylinder cover seen from the top view. As you can see, we have 3 existing diesel injectors here shown in orange, They are on an equal distance around the circumference, and we inject tangentially into the cylinder. And next to the diesel injectors, we have 3 methanol injectors. So the methanol injectors are as close as possible to the diesel injectors, since we use the diesel pilot fuel to inject a small amount of pilot to ignite the methanol fuel. Additionally, the diesel injectors are also used when the engine is running in diesel mode, and then we can run the engine up to 100% load in diesel mode. But then when the engine is operating in methanol mode, we just use them to inject a small amount of pilot fuel. And here in the middle in this picture, you can see a test which we have done on our spray combustion chamber. This shows we have a high-speed camera and an optical access to this spray combustion chamber. This is a test rig which we have, which has similar dimension like an engine, and we can simulate the in-engine conditions. We can have same temperatures, pressures, and similar conditions like in the engine, and we can visually study the combustion, and we can also verify the emissions and the performance of the engine and study the heat release in detail. This is a very important tool to have a accurate development and to accurately being able to predict how this engine will perform, and also in order to be able to optimize the combustion as far as possible. So in this picture, you can see in the small picture, the top one to the left, you can see that we inject a small amount of diesel pilot fuel. In the middle, you see that the pilot fuel is igniting because we have a diesel cycle here, we have high temperatures, and it will self-ignite. Then this small amount of pilot fuel, this will ignite as well the methanol fuel, and we will have then, let's say, combustion of and burn the methanol fuel, as you can see how it's progressing in the later pictures. With the pilot fuel, we can have an accurate start of start of combustion, and this is important to have, let's say, the best possible performance of the engine, since the ignition properties of methanol are not on the same level as for diesel. That's why we have gone for a solution with the pilot fuel for the ignition. Then to drive this, as I showed previously, this is a pressure amplified system, so using engine system oil, and this means also that we need to have a servo oil pump, and the servo oil pump, it can deliver a pressure up to 300 bar. This is a similar layout like we use for the exhaust valve actuation, so it's already a well-known concept since more than 20 years. And the number of pumps needed, this will depend on the amount of oil flow needed, so it can vary from the engine type, engine size of the engine, and the number of cylinders. It can be between 1 pump and up to 6 pumps, additional pumps needed on our biggest engines. This pump can be either gear driven, so directly driven from the engine. This is shown here on the picture to the right. Or it could also be an electric driven pump, which is placed somewhere in the engine room. But in that case, it would need, of course, an electrical power to drive the pumps. In our GTD data, which Marcel mentioned, we already consider the gear-driven pump in the calculations of the fuel consumption in methanol mode. So this energy needed to drive these pumps is already considered. Then for the development, we have been doing the concept design, developing this concept as shown here in the previous slides. We are now completing the detailed design for the first engines. We have already done for the lab engines. We have ordered parts, and we are starting now the conversion of our test engine to be able to run with methanol from the beginning of next year. We start with our test engine here, which we have here in Switzerland, but then we will also do testing later on large bore, and I will show the test engines on a later slide. And the testing on the larger bore will then happen later in next year. Also, with this testing, which we do now, both rig testing and engine testing, we will be able to validate the functionality and the reliability of these components before we have the first customer delivery projects, which is shown here below, that we have the 92 and the 82, and we will first do the validation then on our test engines before it's implemented into those. Here you can see our test engines. This is our test facility here in Switzerland. Here we have one multi-cylinder engine. It's a 4-cylinder engine with a 50-bore cylinder diameter. This is the engine shown here to the right in the picture. This is an engine which we have had already for several years, but we are now rebuilding it and converting it for methanol combustion. Then we also have additionally a single-cylinder engine here. This is quite a recent engine. And this single-cylinder engine we will use for ammonia testing, because we will also develop ammonia fueled engines. Additionally, we also have a number of injection test rigs where we can just verify the reliability and the functionality of the fuel injection system itself. Additionally to the test center here in Switzerland, we also have a similar test center in China, in Shanghai, where we also have 2 multi-cylinder test engines, and one of them we will also now use for methanol testing, and additionally also we have multiple component test rigs, and which we can use now for validating and testing the ammonia. Or the methanol system, sorry. We are also building a new single-cylinder test engine. This is a large bore engine, so it's a 92 centimeter cylinder bore. This is the same as our biggest X92 engine, so it has the same cylinder bore and stroke like our largest engines. And this allows us to do scaling, that we can scale the system from the smallest engine, for which we have test engines here in Switzerland, to the largest engines, and we can see the differences in how the system is performing for a different size of engines. This engine is currently in construction, and we will be able to use it for methanol testing from the second half of next year. And yeah, that was my last slide, and now I think we'll move on to questions. I think you can still add, if you have more questions, you can still write in the chat, and we'll try to answer your questions as good as possible. Thank you.
Thank you for that, Leif. We'll just wait until Marcel gets back on. He's back now. Hello. Quite a few questions have come in, so let's start. For Marcel, can you predict the price of methanol?
Well, I wish I could. I'm afraid I can't. But I think you can find a lot of different predictions with a relatively wide span or range for what the expected price of green methanol will be in the future. I think it's fair to assume that it will be, say, multiple times that the price of what we're paying for fuel today. 2-3 times more, I think, is very likely that it will be in that range. That's why we believe high efficiency will become even more important than what it has been up to now.
Yes, that's very true. Okay, next question is, can we say that the average pilot fuel overload is approximately 5%? I think you addressed this yourself in your slide.
It's a very general formulation here, but at higher loads, it's about 5%. So let's say if you go 75 plus, it's in the range of 5%. If you go towards lower loads, it is a bit more than 5, between 5 and 10, let's say.
Okay. So it says here you've already confirmed fresh water for purging. How about FVT purging? Use of
somebody's been carefully looking at the slide here, I see, which is very good. Yes, indeed, there has been a recent change in which we have now introduced water for purging of the methanol system. As you will see on the slide with the fuel supply system layout, actually the fuel valve train, or FVU as we call it in our case, is going to be purged with water also. So from there to the engine, yes.
Okay. Very good. Thank you for that. So someone's asked, is it correct that in the MAN's case, the FVU is supplied by them and belongs to the engine?
Maybe we should not or don't want to speak too much about our competitors' case. What it is in our case is that the FVU, as I mentioned in the presentation, is actually not our scope of supply. But for the FVU, we will have kind of qualified selected makers that will produce the FVU according to our specifications and requirements. Then this will be delivered to the engine builder, so the engine builders can order there directly, will be delivered to the engine builders and tested with the engine, and then delivered to the yard as a package. So that's how we handle that.
Great answer, thank you. Is the pilot fuel injection only in MDO?
Actually, in our documentation so far, we have mentioned MDO only. There is a change coming with that, as that we also allow to use kind of residual fuel qualities as pilot fuel in methanol operation. So the next update of the manuals, installation manual, will actually see that coming.
Excellent, good. This question is for you, Leif. How do you compensate the lowest volumetric energy density of methanol? For example, do you use a larger fuel buffer inside the injector, for instance, to compensate? And if so, like how much larger must the methanol injector be in comparison to the diesel
it's a good question.
injector?
The lower heating value is a bit less than half compared to diesel fuels. So indeed, we will have to inject a bit more than the double quantity compared to diesel of methanol. But also this methanol fuel injection system, this is a completely separate system, and we have sized it for these larger injection quantities. And so it's taken considered in the design that we can reach also 100% load in methanol mode by injecting a little bit more than double the quantity compared to diesel.
Very good. Again, for you, Leif, do you use a pre-injection and post-injection?
We only do main injection. We have no pre-injection or post-injection foreseen in this.
And do we use a pre-combustion?
This is open chamber combustion. This engine also, they work according to a diesel cycle, and it's open chamber. Both the methanol and the diesel injectors, they are in the same open chamber. So there is no pre-chamber in this case.
Very good. Marcel, will there be an ISA option in the future, or will it be part of the SCR?
Actually, as of now, we fully focus on SCR as an emission abatement technology, because this is very well established on the diesel engines. There is, I mean, technically a possibility to use ICER as an EGR system for compliance. At this moment, we have, let's say, no specific plans to adapt it to methanol engines. But we will obviously monitor, let's say, market demand and charge based on that how we go on with this.
Very good. I guess I'll ask Leif this one. So how do you get rid of methanol slip and formaldehyde?
I think generally we try to minimize the methanol slip and also formaldehyde. That this is something which we are looking into, and it's I think it's a good question, and but also there is no regulation related to formaldehyde, but we are trying to minimize it as far as possible.
Maybe one thing can be added to this also. We have seen from the combustion tests in our spray combustion chamber that there is possibilities to actually optimize combustion in terms of efficiency, but also emissions. And formaldehyde emissions is one of those factors that we take into account here, and we have seen that it is possible by doing a thorough optimization of the combustion with the tool set that we have to minimize formaldehyde emissions to very, very low levels. So I think that is definitely an advantage that we have with our development approach and using the spray combustion chamber technology to develop these systems.
Very good. Have we noticed any efficiency or power increase while using methanol?
Yes, we see that the combustion test which we have done is showing that we have a very good efficiency in methanol mode. This is also because in normal diesel combustion, you are limited by NOx emissions, and this is the let's say the issue. But with methanol, we have less NOx formation in the cylinder. Also, the temperatures in the cylinder are lower. This is one reason why we have less NOx, and this we can utilize for improving the efficiency, since we are not in the same way limited by the NOx limits as with normal diesel combustion.
Very good. And what is used to purge the system after?
Yeah, that's
methanol?
the same as we just discussed before. Actually, I think it's important to understand that after running methanol, the system will only just depressurize and finish. So there is no purge every time that you go into diesel mode. A purging sequence is only necessary in case of a failure of an alarm in the system, or before maintenance, when the system needs to be kind of cleaned out. In that case, we're using water as a purging agent, so to say.
Mm-hmm. Thank you for that. This one is also for you, Marcel. Is the scope of parts identical between the upgrade to methanol compared to a new build?
I guess
I can take
maybe you can take it, but I think it's largely identical. There might be some small deviations, but Leif, maybe you have your.
Yeah, it depends also a bit what is the base engine, but there can be some deviations, and because also let's say that there are some small differences, but it depends a bit on also what engine do we start from, but some small differences are expected.
Mm-hmm. Excellent. We only have a little bit of time left, so we can answer maybe one or two other questions. Let's see. So if the engine should trip between 80 to 100% load, would it automatically switch to biodiesel?
That depends, of course, what kind of fuel is in the diesel system. It can. So if the engine and the fuel system was running on biodiesel before, then it would go into biodiesel operation. But it basically just goes back to diesel mode, no matter the load it trips. But then diesel mode can be operated with biodiesel if desired.
Great, thank you. Thank you so much to our presenters. We've come to the end of our webinar. Just to remind you to stay on, because you'll be redirected to a very short survey where you can opt to have the slides emailed to you. So please stay on for that. We have so many questions that we weren't able to answer in this short time. So what we'll do is we'll collate all of them and see if we can answer some of them to you directly and email those answers out. So thank you very much for joining us today. And
thanks everyone.
Have a great day.
Have a good
Thank
rest
you,
of the
everyone.
day.
Thank you. Bye-bye.